Hi folks, thank you guys so much for joining us. Sorry my voice got out there. So we are going to do derivatives of sine and cosine today. So the first thing I want to do is kind of explore what sine of x looks like along a graph. So what you would do is go to your TI-84. In this case I'm just going to show you on Desmos. I'm going to show you what sine x looks like. And if I was really if I wanted to be specific, maybe I'd define the function f of x to be sine of x. So there's that picture that you'd get on your notes. So basically I just want to find the derivative of sine x. And there you have it. And that looks just about like what we have on these notes, right? So to find the derivative, to find the derivative of any function algebraically, we should use the definition of derivative. For this case, we should also recall a few facts. Now, we should recall that the following pieces of information is true. So the limit as x approaches 0 of sine x over x is 1. And the limit of either one of these, cosine x minus 1 or 1 minus cosine x all over x, that's going to be 0. And then we're going to need one more theorem, and that theorem or property is the, I guess this is a sum of angles property, maybe that's what it's called, but that would have been a trig identity that you would have known back in the day. Now we're not going to use that a ton, but it is going to serve helpful in this proof. So let's use the definition of derivative to find sine of x. Well, the definition of derivative would look something like this. The limit as h approaches 0 of sine x plus some small difference. So we'll call that small number h. Okay? And then we'll say minus sine x. Well, x plus h minus x is just going to give us h. So that is your definition as applied to this problem. So what we're going to use is that third property there, sine of alpha plus beta, sine alpha cosine beta. So let's go ahead and write that in. So here it is. Sine x cosine h plus sine h cosine x. So let me just be clear about what I've written. I rewrote that yellow piece and turned it into this yellow piece as one equality. Okay, so I need to return to my original marker. I need to finish this numerator by typing in minus sine x. It's all over h. Okay, so I know that you guys know how to reorganize terms, but it might not come natural to you to actually reorganize the terms the way I'm going to reorganize them. I'm reorganizing them this way because people before us have already done the hard parts. Okay? So what I'm going to do is I'm just going to show you basically how you can get to using properties 2 and property 1 that I described above. Okay? So here goes. We're going to say that this is the same thing as the limit as h approaches 0. We're going to reorganize these terms. So if we reorganize these terms, I want this sine x to come over here with this sine x. And the reason is because I'm going to be able to factor a sine x out. So, so let's go ahead and just write that. Sine x cosine h minus sine x plus sine h cosine x. Okay, so now that that is taken care of, what I'm going to do is factor out the sine x out of the first two terms. Okay? So, if I factor out sine x, I'll have the limit as h approaches 0 of sine x multiplied by the quantity cosine h minus 1 all over h. And you know what? I'm going to go ahead and break this up into two terms. And there is a limit property that says the limit of a sum is the sum of two limits. So here's my second limit. I'm going to write sine h cosine x and that is also over h. Okay. All right. Well, that looks pretty good. And the reason that looks pretty good is that I have this property. I see that property in the first term, cosine h minus 1 over h as h approaches 0. And I see this property in the second term, sine h over h as h approaches 0. So I know that these properties up here say x, but it doesn't matter what letter it is as long as that letter is the same letter. Okay, so basically I could write this first one as the limit as h approaches 0 sine x. Well, that's interesting. The h and the x have nothing to do with each other, so that's just going to be sine x, right? And then I've got the limit as cosine h minus 1 over h. I'm sorry, the limit as h approaches 0. And then we're going to say plus, and then here's another product. Remember, the product is just the limit of those, the product of limits. So we're going to say limit as h approaches 0, sine h over h times the limit as h approaches 0 of cosine x. Okay, and since that's a product, that h doesn't have to actually come over here. All right, so now let's go ahead and highlight the numbers that we know. We know that this one is 0 from property 2. And if that's 0, then that means that all of this becomes 0. Okay, so all that is just the number 0. So it's like 0 plus, so up here I'll do it in red, 0 plus, and now we're going to come back and figure out what is this. Well, this box right in here, this is just 1. This is 1. And so 0 plus 1 times. Now I need to take the limit as h approaches 0 of cosine x. Well, the limit as h approaches 0, if you go in to substitute a 0 in for h, well, you don't have an h to plug in. So this x and this h, this expression has nothing to do with h. So actually, that limit is just cosine x. So what is 0 plus cosine x? Well, it's just cosine x. All right? So basically what we just said was we found the derivative. We found d dx, the derivative of sine x. And we're saying that it is cosine x. And that is your proof. And your proof will not be needed for, for you to repeat or anything. But the proof is nice because it gives you evidence that it gives you practice. Well, first thing it does, it gives you practice with limit properties, using that product of limits and the sum of the limits. It also gives you practice in memorizing the limit as x approaches 0 sine x over x, and also the limit as x approaches 0 cosine x minus 1 over x is 0. So I like the limit. I want you to learn the limit and love the limit. But basically it's just because I want you to have a little bit of practice with it. Now, if we compare our answers on Desmos And instead of graphing derivative of sine x, if we actually just graph, let's say g of x equals cosine x, you'll notice that that blue and the green graph actually were the exact same graph. All right, so we kind of verified what was going on there. When you look at the next page, you'll see it says if we did something similar for g of x and we found the derivative of cosine x using the definition of derivative, we would get a similar result, but highlight the fact that g prime of x, or I'm sorry, the derivative of cosine x is actually negative sine x. Okay, so there is going to be a symbol that changes there. So on this second page, what I would do is I would just fill in those blanks, and then I would maybe read through this or work through this proof on your own, just to kind of confirm that you know how to do those properties. But that's going to be outside of the scope of this class time. So why don't you take a scrap sheet of paper, see if you can follow along through that proof, or even try the proof on your own, and then go back and check to see if you can rearrange the terms in the right way, and then also use the limit properties the way you're supposed to use them. So anyway, I've done my best to show you guys why the derivative of sine is cosine and the derivative of cosine is negative sine.